Now that we covered what a pneumatic actuator is, how it works, and how to think about it when choosing the best solution for a given task, let's see how we can control it. As it isn't practical to insert a tube to power one stroke, then to take it out and power the other one, the industry has provided the solution in form of a valve. To be able to have tubes inserted in both chambers at the same time, something has to switch between, providing pressure alternatively. For a start, let's think about it like an on-off switch. We want to provide air to blow some dust off the table. When we want the air to flow, we push the button, the air flows, and of course, when we release the button, the flow stops. When buying a blowgun, the trigger is actually a simple mechanism to actuate the movement of a valve. The trigger is simply opening a passage for the air to flow, and when releasing, a spring immediately closes back that air passage. This is called a directional control valve. As we will see, it comes in greater complexity, and the simplest one is the one in the blowgun. When talking about a pneumatic cylinder, for controlling the speed we have to let air bleed out at an adjustable rate for the chamber that is being emptied out. Or, in some cases, we have to let air in at a slow rate in the pressurized chamber. To understand this in a simple manner, we can think at the regular water tap. As we lift the handle more and more, water will flow at a higher rate. If we inverse the process, we can extrapolate that if we lower the handle more and more, we are lowering the rate at which water can escape into the sink. In pneumatics, to be able to do so, we will talk about the speed controller. It lets air flow freely in one direction, usually when pressurizing, and controls the flow rate in the other direction, usually when exhausting the air from the passive chamber. Closes the airway passage. In simpler designs, they are constructed with a poppet. Designing a pneumatic system asks for standardized symbols. Valves have the most variation in symbol, and it is very important to get used to the symbols. Let's take a look on how to build up a symbol and what it means. The universal symbol is starting with a rectangle, which symbolizes the valve. Afterwards, depending on how many positions we want to obtain, this larger rectangle is divided in smaller ones. In pneumatics, it usually is divided in two positions, cylinder advanced or retracted. In some safety applications, in three positions, and very rare cases, more than three. We are calling these positions ways. We will start with the simplest one, the 2-2 valve. It can only be used for blowing applications. So first, we draw a rectangle. We divide it in two ways, as its name says. We now have to show the ports. The ports have to serve a function, so they bear a name or a number. 1, or P, is the pressure port where we connect the pressure tube. 2, or A, is the out port. Now we have to show how the air will flow through both of the ways. On the right, we symbolize with these that the ports are closed and neither one communicates with anything else. On the left, we symbolize with an arrow the direction of the air and the position is activated. In one position, the air doesn't flow. You don't want to blow air. And in the other position, air flows. You blow air. To make the symbol complete, we have to make it functional by adding another symbol for the spring which holds the valve in the normal state. A normal state means that when the lever is not pressed, it springs to the only stable position. This time, it has to be a normal closed valve. Otherwise, it will supply or blow air continuously until pressed. We also have to symbolize the actuation type. I encourage you to take the actuation types on screen, print them out, screenshot them, either way, have it handy for later reference. Now, to be able to power a cylinder, we need at least one more port through which we have to exhaust pressure when in retract stroke. The simplest directional control valve is the 3-2, 3 ports, 2 ways. We add to the last procedure a third port called exhaust, noted R or 3, which, of course, will be necessary for exhausting the air. This time around, both ways direct a flow of air. We will number the 3 ports, putting the pressure and the exhaust on the bottom and the out port on the top. The out port is always connected to the cylinder, or in some cases command needed if the valve is a pneumatic button. Commonly the pressure and exhaust are interchangeable, but for now let's number it pressure on the left, exhaust on the right. Then we have to symbolize the flow direction in the given way. To obtain an equivalent function as the one before, where if you actuate the valve, it blows air, and if you take the actuation away, it will stop the air flowing. We will close the pressure with a V and will arrow the flow from the out port to the exhaust. On the other way, we will do the exact opposite. We will arrow the flow from the pressure to the out port and T-close the exhaust. Now, let's give it a command. Let's say push button. On the other side, if we put a spring, it will be a normal closed 3-2 directional control valve with manual actuation. If we replace the spring and put another button or remove it entirely, it will be a bistable 3-2 directional control valve with manual actuation. It usually is used as a switch for a pressure on a line. As you can see, it is able of both actuating the single acting cylinder and depressurizing it when the cylinder phases are done. Question: what if we used a simple 2-2 directional control valve to actuate the cylinder? You can see that after the transition from the advanced way of the valve to the non-pressurizing way, the cylinder will not be able to exhaust the air, therefore remaining pressurized in the advanced position. Commonly, it is used as the pneumatic button and a control unit for the single acting cylinder. Moving forward, we have to think of a way of actuating a double acting cylinder. It has 2 chambers to pressurize and depressurize, so we need 2 out ports, which will work alternatively. For this, we commonly use a 5-2 directional control valve, but for progression's sake, we will study a 4-2 directional control valve first. The same routine applies. Big rectangle divided in 2 because we have 2 ways. We number 4 ports on the right, 1 or P for pressure, 2 or A for one of the out ports, 4 or B for the other out ports, and finally 3 or R for the exhaust port. Then we symbolize the flow of air with arrows. This works by pressurizing one port and having the other one connecting to the atmosphere. And after the switching of the spool, it is the other way around. So first, we arrow the flow path from port 1 to port 2 for pressurizing the cylinder and port 4 to port 3 for exhausting the passive chamber. On the other way, we symbolize the opposite function, from 1 to 4 to pressurize and from 2 to 3 to exhaust. Now we also have to give this directional control valve a type of command. Let's say double electrical command. We symbolize the commands on both sides of the valve, and now we have a 4-2 bistable electrical command directional control valve. As you can see from the symbol, in one of the ways, the air flows have to cross each other. This, in reality, is not happening, of course, but the 4-port directional control valves are harder and more expensive to manufacture. They are rarely encountered in industrial settings, because the 5-2 valve offers the exact same functioning, but it solves the problem of the 4-2. Okay, now let's see the 5-2. We will have 5 ports, 2 ways, directional control valves. This is the most common valve found in industrial applications. To draw its symbol, we will start with a rectangle divided in 2, because we have 2 ways, then we number the ports. In the middle will be the pressure port 1 or P. On the top, there will be 2A and 4B out ports. And on both sides of the pressure port, there will be the exhausts 3R and 5S. To arrow the flow direction, we start from the pressure and connect it with port 2. Then from the other out port, 4, we go the only direction that doesn't go across, being port 3. And finally, we have to T-close port 5. Now, when pressurizing, the port 2 will receive pressure and port 4 will exhaust to port 3. On the other way, we do the exact opposite and connect port 1 to port 4 for pressurizing the other stroke. From the other out port 2, we will go to the only exhaust available without crossing, which is of course port 5, and we finally T-close port 3. To finish this symbol, we only have to draw the commands. And let's do it like this. On the left, a mechanical roller, and on the right, a spring. This is now called a 5-2 monostable mechanically operated directional control valve. The last types we are going to talk about are 5-port 3-way directional control valves. These valves have the exact base function of the 5-2, but they add a third way in which they have a special function. It can either be a blocked center, open center, or pressure center. Each of the configurations are encountered in situations where cylinder might have to do a supplementary, more particular type of work, or meet some special safety requirements. We will start, as usual, with a rectangle, a bit longer this time, split it 3 ways, and at the center position, let's number the 5 ports. 1 or P for pressure, 2 or A for out port, 4 or B for the other out port, 3 or R for one of the exhausts, and 5 or S for the other port exhaust. Now let's symbolize in the 2 other ways the airflow exactly as in the 5-2 directional control valve. In the right, pressure going from port 1 to port 2, air being exhausted from port 4 to port 3, and port 5 T-blocked. In the left way, pressure going from port 1 to port 4, air being exhausted from port 2 to port 5, and with T-block port 3. Now, we are left with the canvas for all the types of 5-3 directional control valves, which are found on the market. Usually, they are monostable on the center position and have electric command, but you can play with the symbols however you need. Then, contact your supplier and ask them for that type. They should be able to provide any type of command you need. If it is not a monostable directional control valve, then it's a tri-stable directional control valve, and it is manual, no other way. It also cannot have a spring only on one side and be a bistable directional control valve. So, simply, we have monostable or tri-stable 5-3 directional control valves. If it is tri-stable, it can only be manual commanded. Now let's talk about the center. First, it can be a blocked center valve, which means it doesn't allow any air to flow through, neither in, neither out of the cylinder. In symbol, all ports are T-blocked. When in normal functioning, we command the advance or the retraction of the cylinder. But if we take away both commands, then the 5-3 blocked center directional control valve will rest in the center position, blocking all air paths and trapping the air that is already in the cylinder chambers. This will stop the cylinder on a between extremes position, midway, 3/4 down the stroke, a third down the stroke, and so on. 5-3 center blocked gives us the option of stopping the cylinder in intermediary position compared to a regular function valve. To be noted, the position is not kept very accurate, and the load on the rod will move until the pressure inside equalizes the forces. Second, the most encountered type of 5-3 valve is open center. Here we have both 2 and 4 outports connected to the 3 and 5 exhausts, and pressure port 1 is T-blocked. This way is used for safety reasons. When there is a power outage and we, the designers of the machine, have to take into account that the rod has to be able to be moved by hand out of the way, maybe because we have to remove the part inside, or if keeping too long a part in a certain position may endanger the work environment, and so on. The last one, the pressure center, which very rarely finds its way in industrial settings. It can be used to power a double rod double acting cylinder or a rodless double acting cylinder. When in the center position, pressure port 1 is connected to both outports 2 and 4, and the exhaust ports are T-blocked, it pressurizes both chambers and mimics the function of the 5-3 directional control valve. If we use the 5-3 pressure center directional control valve on a one-sided rod cylinder, it will have a mild effect of pressurizing the different constructions readily available on the market. We have to thank SMC International Training for allowing us to use their animation in the development of this course. Firstly, the 2-2 valve, which is a puppet design directional control valve. On screen, we are looking at a 2-2 electric command directional control valve, normally closed type on the left and normally open on the right. So the normally closed valve on the left, unless acted upon with a command, will stay shut, closing the flow of air. It does so through the spring which holds the puppet pressed against the valve seat and opposing the pressure. Of course, when you give the command, be it manual, pneumatic, mechanical or electric, the puppet will move, therefore opening the way for the flow of air to pass through. On the right, in the normally open, things go exactly the opposite. Without a command, the air has a passage through which to flow. The puppet this time is held open by the outer spring. When the command is given, again of any kind, depending on the construction, the puppet will lower and shut the passage of the airflow. In this animation, SMC added an inner spring for the puppet to ensure a proper seal, because it might leak small quantities of air if the movement would not be perfectly perpendicular to the seat. And, of course, when releasing the command, in both versions of the 2-2 directional control valves, will go back to their normal positions. Next is the 3-2 valve, which is a puppet design also. On screen, we are looking at a 3-2 electric command directional control valve, normally closed type on the left, normally open on the right. Of course, as before, when we give the command, be it manual, pneumatic, mechanical or electric, the puppet will move, therefore opening the way for the airflow to pass. As you can clearly see, both the left and the right 3-2 monostable electric command directional control valves are exactly the same, but instead of the usual connection of the pressure to the port 1, which you can see on the left, the pressure tube is moved to the exhaust port 3, obtaining a normally open valve. This is not possible with every construction on the market, so when ordering, talk to your supplier if you are in need of a reversible function 3-2 monostable directional control valve. This valve, of course, works similarly to the previous one. In the normal state, out port 2 and exhaust port 3 are connected and pressure port 1 is closed. After command is given, the pressure port 1 is connected to pressure port 2, which pressurizes the single acting cylinder. When the command is taken away, it goes back to its normal state, where the air from the single acting cylinder is exhausted through out port 2 to the exhaust port 3. If we are looking to keep the single acting cylinder always extended under the action of pressure, then we have to move the pressure tube from port 1 to port 3. And now the valve functions are reversed. Even so, the same ports are connected as before, only now in the non-command phase we are getting pressure from port 3 to out port 2, pressurizing the cylinder, and port 1 is being closed. When command is given, the same as before, port 1 and port 2 will be connected, this time exhausting the air from the cylinder, and port 3, which now has the pressure, will be closed. We are jumping over the irrelevant 4-2 valve, as it is very rarely seen, and the 5-2 directional control valve does the exact same thing and is the most used and encountered directional control valve in industrial applications. Compared to the 2-2 and the 3-2 directional control valves, which are puppet construction, the 5-2 is a spool construction. This construction offers the needed ability to connect multiple ports alternatively. You can see in the animation the two types of puppet design, found in simple 3-2 and 2-2 directional construction, and, on the right, the 5-2 more complex construction. In the simpler design valves, there is only a need for opening and closing an air path. In the more complex design, there is the need to connect two air paths at the same time, but pressurizing alternatively. The 5-2 directional control valve comes in many different sizes and variations, but with the same base design. We have 5 ports. The center bottom one is the pressure port 1 or P, which in initial position sends air to the retract chamber through port 2 or A. And from the advanced chamber of the cylinder, air is exhausted through port B4 connected to port 3R. Exhaust port 5 is closed. At the switching of the spool, the other two ways are connected, so that air from port 1 or P flows to the advanced chamber of the cylinder through port 4 or B, previously pressurized retracted chamber, exhausts the air to port 5 or S through port 2 or A, and the other exhaust port 3 or R is blocked. We can see here a 5-2 bistable solenoid command directional control valve. There is another detail we can observe. From port 1 or P, there is another small airway through which pressure goes into the solenoids. Quick story: in the early development stages of industrial pneumatics, there has been a race to get the lowest powered directional control valves. At the start, there was the need for about 10 watts of power to obtain switching of the spool. Then the race had the 1 watt target. And now, we are down to even as low as 0.1 watts, depending on the size of the valve, of course. This is important as we want to drive these solenoids without power amplifiers directly from ICBs integrated circuit boards, or PLCs, programmable logic controllers. This way, we reduce complexity and needed assembly space. Still, it is mandatory to check the needed command power and the output capability of your command circuit. The solution for this problem is implemented in form of pilots. The solenoids inside act as a micro 3-2 directional control valve, which needs small amounts of power to open an airflow path to pressurize the piston of the spool. As you can see in the animation, on either side of the spool, which move the spool side to side depending on the command given. In most cases, there is also the secondary option of manual switching by pressing the buttons on either side of the spool. Manual command is useful for mechanical check before actually connecting electric power to the solenoids to make sure we have the proper connections, mechanical clearing, and the setup of the machine is done right. Next, let's take a look at the monostable 5-2 directional control valve. In terms of construction, directional control valves are assemblies of standard components with which manufacturers give different solutions. Taking with us the same body, we are changing the right cap and the pistons. Now we have a 5-2 monostable solenoid or electric command directional control valve. As before, we have 5 ports. The center bottom one is the pressure port 1 or P, which in the initial position sends air to the retract chamber through port 2A. And from the advanced chamber of the cylinder, air is exhausted through port 4B connected to port 3R. Exhaust port 5 is closed. At the switching of the spool, the other two ways are connected, so that air from the pressure port 1 or P flows to the chamber of the cylinders through port 4 or B. Previously pressurized retract chamber exhausts the air to port 5 or S through port 2 or A, and the other exhaust port 3 or R is blocked. One question we might ask is, where is the spring that returns the spool in the initial position? If we look closely to the right piston, we can see it is always pressurized. Because of that, the spool is always trying to get to the normal position under the action of the pressure. We are calling this a pneumatic spring. And when the other command comes in to pressurize the other piston spool, it opposes the force and overcomes it. Look at the difference in size between the two pistons and you'll see the commanded one is bigger and will be able to push against the smaller one. We are calling this differential command. Another detail to look at is the way air reaches the command piston. It goes through a poppet solenoid valve and afterwards pressurizes the chamber. When the command is taken away, the air is redirected from the piston chamber to the other side of the piston. We of course need to depressurize the chamber so the pneumatic spring can push back the spool in the initial position. There is a very clever solution not to overly complicate the construction in form of a special gasket which seals one direction and lets the air flow in the other direction. This allows us to route the air from the command chamber to the exhaust port R3. There are other controls of pneumatic actuators and some other functions we need to talk about. Most important is cylinder output force. This one we'll cover a bit later in the FRL group. But we also have to control the speed. Some applications need to transport parts from point A to point B as fast as possible to cut up times. Other times, we have to hold parts very well or to transport thin parts which can bend from the flow of air when moving too fast. So the need for speed control is real, and it is done by using a speed controller. On the other hand, if we want to obtain the highest speed possible, we will use a quick release valve. We also have binary functions, which have to be accomplished for safety or for proper phase achievement. Let's say we don't want to let pressure actuate a cylinder if the door of the machine is open, or if the user doesn't press two buttons at the same time. These are valves with binary functions, or AND. There have been developed more advanced functions, but they are not in demand anymore. Thanks to development of electrical controllers, which are more adaptable and easier to modify, not needing a mechanical modification. To understand the concept of cylinder speed controllers quicker, we will first talk about each component which makes it. First, there is the check valve, a component which lets air flow in one direction and it doesn't let it flow in the other direction. It has a seat in which a ball can sit perfectly to stop any air from flowing if it comes in one direction, and lets the air flow freely in the other direction by moving the ball away and creating a path for the air to flow. At this symbol we can add a command which lets us unlock the flow of the valve with another pneumatic command for the air to be able to flow freely in both directions. We call this a pilot-operated check valve. Secondly, like the water tap, we have a pneumatic component which lets us control the flow rate. It is simply a screw which restricts more or less, depending on our setting, the cross-section through which air can flow. The symbol is one of a line which represents the tube of pneumatic air, a flow restriction with a curved line on either side of the line, and an oblique arrow which symbolizes the fact that it is adjustable. This is called the adjustable flow control valve, or simply the flow controller. Now that we understand the base valves, we can unite them like this. A flow controller, in parallel with the check valves, gives us a speed controller. This component will modify the airflow in one direction, the direction that is blocked by the check valve, and air is able to flow only through the flow controller. When air travels the other way around, it will pass through the component freely, unlocking the path of the check valve, and even a little bit of flow will go through the flow controller. Let's see it in action on a simple pneumatic circuit. I encourage you to download a free version of FluidSim from Faststop Pneumatics and play a little with each component to understand it better. First, we'll control the advanced speed of a double-acting cylinder. We are doing this by controlling the exhausted flow rate. By limiting the flow of air going out, we create a back pressure which holds out the piston to adjust the return stroke. It will be the same procedure. And if we want to adjust both the advance and retract speeds, we need to mount speed controllers on both sides of the cylinder. Now, to adjust the speed of the single-acting cylinder, we cannot limit the exhausted air, because there is no port available to mount a speed controller on the spring side. In this case, we have to control the airflow rate that goes into the cylinder. For this, we mount the speed controller flipped to adjust the flow rate that goes in. To adjust the retract speed of the cylinder, we will have to be able to adjust the flow rate exhausted. We just switch the orientation of the speed controller so we can limit the airflow coming out. And if we want to adjust both the advance and return speeds of the cylinder, we have to mount two speed controllers in line with the ball facing each other, not the valve seat. Most of the speed controllers available on the market are designed to mount directly on the cylinder. And in this case, they have a particular function which relates to the threaded end. They are divided in meter in and meter out. Meter out speed controllers adjust the flow rate which goes out of the cylinder from the threaded side and lets air flow freely inside. This is used the most. About 80% of the speed controllers are meter out. This is because it will adjust the speeds of the double acting cylinders and rotary actuators, and it also used to adjust the return speed of the single acting cylinder. Meter in speed controllers, on the other hand, adjust the air going into the cylinders from the tube side and lets the air going out flow freely. It is used only for adjusting the advance speed of the single acting cylinder. Out of all speed controllers, they are found about 10% of the time. The last 10% are inline speed controllers, which have the same ports on both sides, giving us the possibility to change their orientation. In the futuristic industrial environment, we can see coming in fast, automated control of the processes is going to be more and more easy to manage by less and less specialized people. But there are also simpler processes which can be designed very fast at a very low cost directly with binary pneumatic logic. These are a series of valves which engulf binary functions found in electric command, low-level program development, and ICBs. 1. We have a simple pneumatic cutter manually fed with parts. Here, a worker has to put in the parts, then press a button for the cutter to actuate, and finally, the worker has to collect all the leftovers. The concern here is about safety. We do not want the worker to press by mistake the command button and actuate the cutter while he is handling the part. Even more so, some workers are courageous enough and will hold the part itself in front of the blade for speeding up the process. To eliminate human error, or human, let's call it, bad decisions, we'll have to implement a safety function in which we are making sure that our worker will have both hands occupied while the cutting action takes place. He will need to press the buttons simultaneously to actuate the cutter. The buttons also have to be at an enough distance from each other so that the worker cannot press them with just one hand. To do this, we are using a binary function valve called the AND valve. The symbol is constructed by drawing a rectangle with two inputs X and Y and an output A. Inside we have four vertical lines which symbolize the valve seats. Between these lines we have an H-shaped valve which blocks air from reaching output A if the signal comes from only one of the inputs. This is a table for the function of the AND valve. Let's try it. I also encourage you to do it along in FluidSim. Let's give it no signal, no X, no Y, so A is not transmitting a signal. Next, we give signal X, but not signal Y. Still A is signalless. Going forward, you only give the signal Y, but still A has no output. The only way A will have an output is by having both signals at the same time. So signal X and signal Y gives us signal A, which in turn activates the main directional control valve and pressurizes our cylinder to cut. This is happening because if only one signal is coming in, the edge inside the valve will close that side of the air path, and only when both signals are present, there will be an air path open for the pressure to reach our target. Of course, If we take any of the input signals away, the output A will be cancelled. We have to add that even if the AND valve is practically useful, this binary function can be obtained by simply connecting the input signals in series. Let's take a quick look at that. We have two pneumatic buttons, X and Y. If we pressurize only one of them, say the Y one, from the out port 2 or A from the bottom, we take the pneumatic signal to the pressure port 1 or P of the X button. Now, the output port 2 or A of the X button will be the result of the binary function AND, which of course means that only when we press both buttons the airflow can go through the entire path from pressure source all the way to the command of the main directional control valve to actuate the cylinder. Now, the other example where binary pneumatic logic is coming in useful to quickly solve problems. We have a pneumatically actuated door, which is always shut. We still want to be able to open the door from both sides, of course. For doing so, we are using a shuttle valve. The shuttle valve is symbolized with two V's opposing each other, similar to the check valve. In between the V's, there is a circle that represents a ball, which acts as a blocker for the air path when air is coming in from only one side. The function of the shuttle valve is called the OR binary function, or simply OR. This is the table of the OR function. Let's try to verify it in a simulation. Please follow along in FluidSim if possible. When neither of the inputs have a signal, the results are 0. If we only give signal X and not signal Y, then the output A transmits the pneumatic signal. This is the same the other way around, if we only give the Y and not the X. And when we give both signals, port A is still outputting a signal. By pressing either one of the buttons, we can transmit the command to the main directional control valve and actuate the opening of the door. Those with more experience in the electric command circuits might be asking, why do we actually need the shuttle valve to have the OR function? As before, with the AND valve, where we could simply connect the buttons in series, we could here connect them in parallel, right? The answer is that with pneumatics, air would just escape through the other button and the signal would not reach the target. So the OR function in pneumatics can only be obtained with a shuttle valve. You can try it in a fluid simulation, but it unfortunately doesn't show the reality. If you have the opportunity to try it out in real life, you will observe the problem. Meanwhile, you can be confident